Thank you so much for the introduction. Pleasure to be here. Um, we'll start the talk. So the talk is about if you are doing anything within natural language processing, you probably are interested in BERT. And if you are actually doing something like developing something and taking it into production, then you would care about things like latency and how fast it is go and user experience and everything. And then you need to accelerate the whole process, and that's what the talk is about. But before I go ahead, I'd like to have a quick poll on who all is familiar, heard about BERT, or used BERT. Can I have a show of hands of anyone heard of BERT? BERT? Okay, awesome. BERT. Okay, like about 50%. That's great. Okay, so before we go ahead, we have a demo. But let me talk about why we are interested in BERT in the first place. So last year, there was a revolution within the NLP community, and BERT made that happen. All the natural language processing applications took a huge leap in accuracy, surpassed human benchmark levels at many of the data sets, and BERT made that possible. So yeah, so that's why BERT deployment. Okay, so let me go and show you one of the applications, which is question answering. So why question answering though? So what would you do to evaluate if somebody had understood you or somebody understands some content? What do we do? Ask questions. Yes, we ask them questions to evaluate their understanding, and we use the same strategy to evaluate machines as well. If machines are so good at NLP, like why don't we just ask them questions and see how they do? Thus, the question answering application is a hugely popular downstream task within the NLP, and thus we will look into it. Okay, let me quickly go to the, so we have an AWS instance set up, everything ready to go, and we just want to show you an example. What we have here is a passage about TensorRT, and if we execute in the ready to go GPU accelerated instance, it will ask us for a question. This is the passage that we have. And let's say I give it a question, what is TensorRT? And then it is able to give me the answer immediately. It's a high performance deep learning inference platform. Where does it get that from? It gets that from right here. So it basically understands what I'm asking. And we could go on asking more questions, and we'll hopefully do that more at the end if we have time. Is this viewable though at the back? Is this good, the size? Okay, awesome. So that's what the question answering task is. You have a passage, and then you can ask any questions about from the passage, just like we had back in school. So that's the application. So what do you need to know if you are if you're interested in NLP, trying out BERT, GPU accelerated? Yes. Okay. Okay. Cool. So there are mainly three things that you need to understand or need to know, like a little bit, which is basically you need to know a little bit about BERT, and it'll help to know about TensorRT, the toolkit, the deep learning toolkit from NVIDIA, which helps you accelerate any deep learning models. And thirdly, the optimizations that we did with on TensorRT to accelerate BERT. And while we do that, we will be this is not working. Okay. Yeah, while we do that, we will be deploying. Sorry, this is funny. We will be doing the whole process from scratch. Whatever you just saw in the demo, we will be starting a blank AWS instance and set up the whole process in the next 15 minutes or so to show you that it's super simple. So let me talk briefly about BERT. This is a NLP language, deep learning language model deployed last year, which, as I said, helped jump accuracies on many tasks. And let me talk quickly about some of the key terms that you may have heard if you're familiar with BERT or deep learning, transfer learning. And BERT is the first, one of the first that introduced transfer learning within the NLP community in a large way. And how it did that is broke down the end-to-end learning process of a particular task into two things. First is the pre-training, where you have a huge body of text, for example, Wikipedia or books corpus, and the language model goes over all of the text and gets understanding or builds its understanding of the language. It'll see the semantic relations between words and understand the grammatical structure. And so basically, that's just building the language model. And we have seen language models before. For example, it started back in like decades ago with n-gram models, and then we had RNNs and LSTMs. This is similarly a bigger language model. The step after pre-training is fine-tuning. So you have the huge language model built, and then you want to apply that or use the embeddings from there, just like Word2Vec embeddings. You use those embeddings for your downstream tasks, such as it could be like question answering, the one that we saw, sentiment analysis, named entity recognition, sentence classification, you name it. So that would be a fine-tuning task. So it broke down the whole process into these two steps. And it achieves the training task. One of the new things that it did was using the masked language model. So kind of like took that body of text, removed some words from there, and let the model predict what those words would be, kind of like masking those words out and let them predict. And also next sentence prediction. Given two sentences, does one sentence follow the other? So that way, doing those things, it was able to learn it in an unsupervised manner. Thus, the pre-training step is unsupervised. It can just learn from a body of text, no annotation required. And the fine-tuning is a supervised task where you need to have annotated data set. These are all done on top of the transformer encoder layer, and it's also using multi-head attention, and many such things, which we will need probably hours to talk about. Oops, this is being funny. Okay, so this is like the whole pipeline of how you would use BERT. If you are just using the pre-trained checkpoints, which are open source by Google when it came out, you can just download them for the TensorFlow one, or if you're using PyTorch, can do that from Hugging Face. So you can just start using the open source pre-trained checkpoints. Or if you have a big body of text, or let's say you have your own company data or your user data, and they're like quite huge, and you want them to pre-train on that, you can use this strategy where you start from the pre-trained checkpoints, pre-train on those texts, and you will get your custom pre-trained checkpoints. So it uses the open source one, and also you can pre-train on it. And either of the options, that your next task would be to fine-tune for a particular task. So let's say you are trying to do sentence classification, then you would probably need a sentence classification annotated data set. Or let's say for the question answering task that we just saw, that was fine-tuned on the SQuAD data set, the Stanford question answering data set. So once you do that, then you will have the fine-tuned checkpoints. And this checkpoints is good enough for you to do any kind of inference. But then if you want to accelerate the whole process, because if you do this and run it on, let's say, CPU, it's going to be really slow. But even if you do it on GPU, it may not meet your latency requirements. That's when TensorRT comes in. TensorRT would take those checkpoints and create a BERT engine, which you can use to, like TensorRT BERT engine, which you can use to do the inference. Yes. Checkpoints would be the set of weights that you could think of that as the learning of the whole model, basically. It's like a huge tensor or matrix, multidimensional matrix that has all the weights for given your input, what are the output classes or the possibilities, basically. Yeah, so it basically maps the input to the output. That's the checkpoint. Okay, so next we will look into TensorRT, and I'll let Eddie take from here.
You want to go ahead and start the demo?
Oh, yeah, okay. Yep, okay. Sorry. Actually, so while we are doing this, we would want to build from the very beginning. Let's see. This is a blank AWS instance powered by Volta. What we are going to do is So these are the 4 steps that you need to run. This is one of the blogs that we published like a month ago. We just want to show how simple it is to set this up if you want to do it on AWS. So we'll just pull the repository first. And once it is done, we would want to build the container. Container makes our life easy so much. So anyway, this is, we are pulling it from one of our NVIDIA repositories. And you can find many other models there along with this BERT model. So this will take a little bit of time while I let Eddie go over the process and go over the next, like talk about TensorRT. Do you want to make this full screen?
So as Pranendu mentioned, we have our BERT model. It's a very large model. And we want to deploy that on AWS. So there's latency requirements that we have to meet. There's other requirements, bandwidth, things like that. So the idea with this software that I'm going to talk about, TensorRT, is that we take that model and optimize it as many ways as possible. So what NVIDIA has is this library or framework called TensorRT. So it can take from any of the deep learning frameworks, any model, for example, this BERT model, run it through TensorRT and deploy it on any of our GPUs. So this includes anything from an AWS Volta to all the way down to an embedded system like one of our Jetson platforms. So what's happening inside of that, there's a couple of ways that it actually optimizes any of these networks. So a couple of the important ones, which will lead into what we actually did, was layer fusion. So if you can think of how large a deep learning network is, you want to fuse some of those layers to make the network smaller. There's precision calibration, which is taking your model from floating point 32 values to floating point 16 or int8 to make the calculations faster. Or things like kernel auto-tuning. So for our different GPUs, we have different low-level libraries that work slightly differently on each one, slightly optimized for each hardware. So TensorRT is going to look at what operation you're trying to do and optimize for your specific piece of hardware. A GPU. So a GPU is a graphical processing unit. So it's basically a co-processor to a CPU. So to start with, they were just used for graphics, for gaming, things like that. But in the past 10 or 12 years, we've decided to transfer that to more mathematical computations, things like that. Yep. Mm-hmm. Yep. Yep. Mm-hmm. Yep. Mm-hmm. Yep. Yeah, so we have a slide right at the end for performance, but just to give you a preview, we went from a CPU node, a full entire CPU node, in about 45 milliseconds to about 2 milliseconds in our inference time with GPU. Yep.
So you mentioned that it optimized for your specific hardware per
Mm-hmm. Yep.
Does it optimize for your that user request side? I mean, if based on like certain way that the user is asking, you learn more from the experience. I mean, do you have any caching information that accelerate the performance?
Not that I know of. We have another product called Inference Server, which is basically what you're talking about. That's not what TensorRT is doing, though.
So that would be another layer on top of TensorRT then?
Yeah, so it's using models developed with TensorRT, and you can do things like that.
If I may add to that, so when you are sending in a request from the front end side, all your processing is happening in the cloud, on the server in the cloud, right? So this is deployed in there. If it's a GPU-enabled server instance, you can, or any model that is running on that deep learning model, you can optimize with this TensorRT. But it doesn't do on the front end side, but all the processing that is happening on the server side. Yeah.
Yeah, my question is really more like who is processing, that optimization kind of request going into your TensorRT, right? I mean,
Okay, so you will probably have a web server or something like inference server, which will send that to this. Yeah.
Okay. So with all of these optimizations, I want to talk about the specific ones that we did for BERT. Before that, let's see if our, looks like we're still building, so we'll keep going. So there's a couple of different optimizations that we did based on some of the layer fusion and kernel auto-tuning and things like that. So the encoder block of BERT, which Pernendu talked about before, looks like this. So inside of that, we have multi-headed attention, which I'll get into in a minute. We have a few other deep learning type layers, so a fully connected layer, skip layers, layer normalization, and then activation functions. So one of the things that I talked about with TensorRT was layer fusion. So the first thing that we did was actually take these residual layers and the layer normalization and fuse them together. So the reason we did that is to make them into one GPU kernel rather than two. So we don't have to communicate back and forth with memory, which makes that a little bit faster. So secondly, we looked at this activation function. So one of the cool things about GPUs is that they're really, really fast at computation. If you give it enough computation, you're going to see the speed up. The bottleneck is usually communication, so feeding it enough information. So the idea here is instead of having to use all of these variables, A, X, B, all of them, store them in memory, and each operation go to that, we're going to fuse them all into one kernel for our GPU and do all the operations on one memory cycle. So the idea is instead of doing one result, storing in a memory, doing the next result, storing in a memory, we're going to do all of these in parallel, storing in a register. And then the last optimization that I want to talk about is for the multi-headed self-attention, which we're actually getting the biggest speed up for. So this is actually what's inside of that multi-headed attention. So again, we have fully connected layers, which are typical deep learning layers. We have a transpose operation and then a few other smaller operations here. So what we're going to do is actually fuse these together like so. So we're going to have one big fully connected layer, which gives us the computation that we want. We want to feed it with more computation. We're also going to fuse that transpose layer. And then down here, we're actually going to fuse the element-wise scaling and the softmax. So that is actually the smallest part. The biggest speed gain we're seeing here is from fully connected to transpose. And this is a little bit of the performance. So this is from a full CPU server to one of our GPUs, a T4. The instance that we're running on right now has a Volta V100 in it, so it's going to be a little bit faster than this. So, yep. Mm-hmm. Yep, so we have a C API, we have a Python API, and you just create your model. And what happens behind the scenes is it does all this optimization. So for the key takeaways and the rest of the demo, I'm going to pass off to Pernendu. Make sure that, yep. Okay. So while Pernendu is talking about the key takeaways from this talk, I'm going to.
Yep.
I'm going to go ahead and start building the TensorRT so we have something to play with whenever he's done.
So here what Eddie is doing is basically the code that we pulled in at the very beginning. He is building those examples. And also this is going to pull in the fine-tuned models, the one that we talked about. It's pulling it from NGC, which is our container repository, but it also has model scripts and pre-trained or fine-tuned weights for many of the models that you might care about. So that's what is happening here. It's pulling down the weights. And next we will build the engine once this is done. Let's go to the slides. Okay. So what are the primary things that you need to know from today's talk, like if you ever were to do an NLP thing? First is state-of-the-art inference speed in NLP tasks. I mean, if you are doing NLP today, it's definitely something transformer-based. Okay, BERT is one of the state-of-the-art today. There is Roberta, XLNet, GPT-2, but all of them are based on transformers. So if you are doing that, you would probably want this. So what we have done is taken the BERT, so it's made it optimized such that you can use it in your production applications. Any kind of conversational AI application, you wouldn't want the user to you wouldn't want the user to wait. Like, let's say they type in a question, otherwise they will have to wait a few seconds, which is not great user experience. Let's say you are building a chatbot, you wouldn't want the user to wait for your optimized answer, the best answer, because this gives it a high leap in accuracy. This also takes a lot of time. So that BERT it's possible in production now. It's a 2.2 milliseconds for downstream tasks. All these optimizations that we did are open source. That means that you can take this for any other downstream task. Question answering, sentence classification, entity recognition, you name it. There are like 20 such tasks. And this is very simple to set up, as you are seeing. TensorRT does the job under the hood. All you need is like a few commands to use the API. So let's go back and see where we are at. So this is the last step where the engine building is happening. What it is effectively doing, like you saw in Eddie's slide, that we have a whole lineup of GPUs, like Volta, T4, and it started back from like Pascal and Kepler. But then this works any of the recent GPUs. It'll optimize your. So what it is doing is looking for the most optimized kernels within the GPU, which will run best for your application. That is what it is doing. Yes, we are building towards it. What we want to show is like it's basically, if you want to replicate this, it's just running 4 commands. We have abstracted all of the complexities away. Let's go into the slides. One thing that I want to show what is happening here is basically this step. This is the step that we are currently at. It's building the previous one where we downloaded it from the NGC and it downloaded the checkpoints. This is the building process. Next, we will just execute it, which we did at the very beginning. Yes. Okay. That's a great question. Let's say your text is very big. What you would first want to try out, like, depends on how big it is. Let's say if it's worth like 1 A4 page, it should do fine here. Although there is some bounds within how big of a sentence you can fit, and the strategy that is usually used is like chunking. So you would break down your passage into multiple queries, and then whatever the answer comes out, they will be summed up to give a bigger answer. So some of the implementations already have it implemented that you will do the chunking process. It has a sequence length, which is basically bounding how much time it takes to do one inference, basically. So, but with chunking, you can do any length of text. Yeah. Okay. Yes. Yes. So then you would need some strategy like information retrieval. So you would have to get this running along with some information retrieval thing. So what the IR pipeline would do is, what are the top few documents, like top 2, top 5 documents that would be most relevant? And you can use BERT for that task too. And once it gets those documents, then you will find the exact answer from within that. Yes. To Poly? I am not sure about that. Yeah. Do you know about that? Okay. Okay, let's see where we are at currently. Okay, so. Okay. Do you wanna go and run this? Okay. So this is where we build the whole. Let's go ahead and run an example. And this is the same example we are running, and we can see that it is able to produce the answer similarly. And you can try it with any other example that you have in mind. So let's say we can ask it any other question. let's say who develops, this would be an ambitious one. I'm just trying it right on top of my mind. Who develops TensorRT? It is an ambitious one. Let's, I mean, I would ask it for the people, like, could you come up with a question for this passage, and let's see if it works? I mean, is it there? The answer has to be there, though. Okay. Okay. What is NVIDIA? Uh-huh. It's, yeah, if NVIDIA is not there, it's not going to work. Let's see. Yeah, so it gives that answer. If the answer is there, it'll give the answer. But if it's not there, it'll respond. Yes, you were having a question? Is that answer there?
Yeah.
Yes, okay. Sourcing. Oh, sorry.
While he's showing this example, are there any final questions?
I don't think this is working, but
Sorry.
Yep.
Mhm.
So if you have these pre-trained, pre-trained, you have this model, and you want to have different versions based on fine-tuning.
Mhm. So again, so we have an inference server that actually does that. I think it's the same. So you can run actually different models inside that inference server. Yep.
Okay. So yeah, that'll be it for our talk. And if you have any further questions, we'll be happy to take them.